No.
Okay. You can find them by going to the course webpage. And there will be links labeled as recording underneath each day after they happen. So, I'm not saying that you should have watched the recording already, since you were in class, but if there's a day that you want to see specific things slower or faster, you have access to them. Cool. Nice. So, we were in the process of just studying some naive set theory. We have some operations, intersection, union, containment that interact in some ways. The last thing that I want to do in this particular section of notes is just state some properties that will intuitively be clear, and we'll prove some of them. So, here's the first one. Let's think about the operation of intersection and union. I assert that for absolutely any sets, the intersection of the two sets is contained in either one of the sets, and that set is contained in the union of the two. That seems intuitively true, right? Or like if you wanted the Venn diagram argument, you would just like draw the picture. Yeah, everything in the intersection is in A. Everything in A is in the union. Great. That's not a proof, though. What do you think? Shall we go through at least one of the proofs? All right, there are two containments here. Let's prove at least one of them. Let's prove either that let's go in order. Let's prove that the intersection is contained in A. If you want to prove that A intersects B is contained in A, well, this is a proof of set containment. We'd better start by considering a thing in the smaller set, proving that it's in the bigger set. So, let's do it. Let's consider any x in the intersection of A union B, and aim to conclude that x is in A. What does it mean to be in A intersect B? Yeah. All right, so how would you want to go from that to just concluding that x is in A? Better? Okay. Well, have we just already stated that x is in A? Oh, great. So, in particular, have we just proven that everything in A intersects B is in A? Awesome. Yeah.
Is that the set of A symbol there in the last line there?
Is an element of.
Is an element of, that's okay.
Yeah. My handwriting just got moved. What do you think? Is the proof of the second bit going to be basically the same? Except instead there will be an or that shows up at a different stage. Cool. So here are some other properties of intersection and union. If you take a set and union it with itself, what do you think you get? A union A should be?
A?
Yeah, probably. What about A intersect A?
A?
Yeah. Right? If x is in A, then certainly x is in A and x is in A. Right? You can say the same thing twice. It's just as true. Commutativity. And the name of the property should give you a hint about what the conclusion will be. A union B is the same as if this is supposed to commute. B union A. Seems believable. All right, that's generally what commutativity means. This line is saying that these set operations are commutative. There is an associative law for intersection and union, which fundamentally means that you don't really need to write those parentheses. Associativity would say that A union B union C is the same as A union B union C. Same thing with intersect. And you'll notice that as I go through and reread these, I'll notice typos like commas that shouldn't really be there. That particular typo doesn't matter, but there will be typos that do. Distributivity. Oh. Before I go on, I know you've been walking on the iPad anyway, but I know you have it. We're very nice. You can use whichever one you want. Oh, maybe I'll even ask. Kind of people feel like they'd rather take notes on an electronic copy that they have on an iPad.
If I have an iPad.
Yeah, okay, sure. You're welcome to do that if you want. The only caution that I'll give is I'll occasionally update the PDF, which will be mildly annoying. I'll have to keep track of maybe which date they're taking notes out of. And finally, distributivity. These operations distribute over each other, in that A intersect B union C is the same thing as A intersect B union A intersect C. A union B intersect C is those statements all make reasonable sense. And now, well, the most that I'll want to prove is one of the distributive laws. And maybe we'll start by even just like drawing a picture of the thing. If you have this triple of sets, let's just try to draw the two things. We'll see if we even believe the statement. A intersect B together with C. So see, A intersect B would be this much. And there's the set C. So it looks like right now everything shaded is A intersect B union C.
So in this case, it's everything that qualifies for any of the conditions in the statement there? In the sense that, like...
Yes, that's what union should mean, right?
Okay.
Right, this is... union means. So let's try the same thing over here. Let's start with A intersect C. So A intersect, no, A union C is all of that. I would like to intersect that with A union, oh, that should have been B. No. It's not written in the city. B union C is, would have been better off with an additional colored pen. So I want everything that is simultaneously in both of those crosshatches. Does that agree with what this says? Yeah, great. I think I believe it. Let's come up with a clue. So, let's show that A intersect B union C is equal to A intersect B union A intersect C. And I think the letters don't match up what I did here. Yeah, that's okay though. Well, I guess we need to show two set containments. Let's start by showing this is contained in that. All right, so how should a proof of set containment like this start? How do you show a second? Yeah.
You want to find X in like one of the conditions and then just sort of keep adding them belly and then just put it sort of verbally on the page?
That's not how the logic's going to go. It's like this union will somehow transform into an OR. So then I'll have like two cases. But that's like one step into the proof. A very fast line in any proof of set containment is you want to show everything in here is in there. So if there's no like deep step right here, consider any element of the set. That's the way any set containment proof should begin.
Okay.
Wow. Unless you're using something fancy. Now let's do that. So there's a union there. What does it mean for X to be in the union of two sets? Yeah.
X is in both sets?
Union, not intersection.
Oh, it's in either set.
It's in one or the other, or maybe both, but OR already does that. So, X is in A intersect B, or X is in A intersect C. So one of two things must be true. Possibly both. Does that make sense so far? Right, that's what union means. Well, now there's like, I know that one of two things is true. So maybe there's like a case-wise proof. So, case 1, suppose X is in A intersect B. I would like X to be in this set. So let's look at what the goal is. How would you, so if you want to show X's in that set I'm aligned to go as, that's an intersection. So I need X to be in A and X to be in B intersect C. So let's try to prove those two things one at a time. X is in A intersect B. How would you show that X is in A as a consequence? What's like a path that goes there? Yeah.
Either or X is in A at that B.
Yeah.
Yeah, let's write down all of that. Then X is in A and X is in B. And we already have X's in A already. So we just need X to be in B union C. All right. So given the two things that are just written, how do you get X to be in B union C? Yeah. Yeah. As X is in B, maybe I'll add one clause right here. B is certainly a subset of B union C. Yes. So since X is in B, and B is a subset of B union C by proposition 1.1.1 above, X is in B union C. As X is in A and X is in B union C, X is in A intersect B union C. So is that everything I need? Does that complete the proof of this set containment? What is lacking? Yeah, there's the other case. Do you think the other case will probably be pretty similar? So maybe I'll even take advantage of that. So that in either case, X is in A intersect B union C. Have we just proven a set containment, assuming that you believe the similarly line? I think so. We considered any X in one set, we showed that it's in the other. We conclude that X is in. We conclude that A cap B union A cap C is contained in A cap B cup C. How did that proof feel? So I think for the second half of the argument, the reverse containment, maybe I'll suggest one of three paths from here. One is I can talk through that proof, but maybe you're getting tired of my voice. The second option is I can just be quiet for 5 or 10 minutes. You can talk through this proof with those around you. 2 of you are missing table mates, but happily you're pretty close to each other anyway. And the third option is it can be skipped and we can just move on. So let's just see a show of hands. How many people would like to see just me talk through the proof? Okay, a few. How many people would rather talk through the proof with those who are around you? Oh, well, no hands. How many people would rather just see it skipped? All right, well, I think the majority plurality had me continuing to talk. So here's what I'll say. If you want to walk through the proof, and even talk reasonably quietly with those around you, go for it. Let's talk through it, though. So the next step is to show the other containment. A intersect B union C is contained in so we better consider any element of the allegedly small offset and show that it is an element of the allegedly big offset. That'll do. And maybe we'll even sketch it. Let's figure out the logic before we even begin. We want to go from X in let's come down from the top. What does it mean to be in this intersection?
It needs to be simultaneously in the set A and the union of B and C.
Cool. And the only bit that's complicated looking there is this. So, as long as I'm being just sketchy, let's sketch. What does it mean to be a B union C? Yeah.
Should be origin C.
Oh, neat. So this looks like cases. Case 1, case 2. So let's say case 1. Let's assume that X is in B, and let's try to get down here. And maybe it's useful to figure out what the hell we even need to show. Let's look at this conclusion statement and try to parse this out. So what would be enough to make you happy if we wanted to show this?
Yeah. X is in A intersect B or A intersect C.
Some parentheses, so I think we're going to chase that down. What does it mean to be another of those two intersections? Yeah.
That X is in both of those sets.
Yeah. X is in A and X is in B. Is the handwriting is the bold writing big enough for everyone, or should be a little bit less? Okay. Alright, cool. So, now let's look in this case 1. So if X is in D, how would you go from the things you know to the things that we apparently want? Yeah.
And we have X is in A and X is in D, which is the first condition below.
Oh, neat. If a thing is true, then a thing or something else is true. That's groovy. So do you think we have like enough written down there that we can just write down the proof now? We have the ideas? So X is in A intersect B union C. So X is in A and X is in B union C. Since X is in B union C, one of these two things is true. Yeah.
You still need the second case there?
Yeah. So let's continue to be sketchy. Case 2. So if X is in C, how could you get this conclusion? So if X happens to be in C, let's look in here. So we already have X is in C. That's nice. Do we already know that X is in A?
Yeah.
Oh, awesome. That's supposed to be like a ditto verb, basically the same sentence written again. Right, you wouldn't want that in like the formal write-up, but this is the formal write-up. Cool. So in either case, do you think that this logic flow should do the job? Awesome. Let's try to write that down. Now, it may be like writing on the board like this when I've like given you paper to begin with is slightly unfair. It is often useful to have just additional paper in this class for exactly that reason. I'm going to walk things out aside, which don't really belong in the notes.